Oh, yeah. Good. Okay.
Hi.
Awesome. So we're glad to have you here bright and early for the critical design review of our collaboration with Acute Design as we work towards the goal of creating affordable Braille displays. You're already very familiar with our team, so I won't waste too much time on introductions, and we'll get right into what we want to share with you today. So the presentation will start out with a brief recap of the problem at hand, and then we'll quickly touch on the user needs, requirements, and project constraints that have changed since our last discussions in the PDR. Once we get those details out of the way, we'll move right into the hardware and software solutions we want to implement in our design, and these will consume a majority of the presentation. Once we finish up, we'll talk about what we were able to complete this semester and some things we didn't get to and how that influences our plans in the spring. And then finally, we'll conclude with some lessons learned for better or for worse, and how we're going to use those to be more productive in the next semester. The project aims to learn from a sponsor's previous design to create an improved Braille display that is cost efficient, reliable, and portable. And we believe that if our solution meets these needs of the user, that the equal opportunity of blind people in the workplace will improve as a result of using our displays.
Now, our requirements table here has relatively just been the same throughout our research and development, but one dictator of our progress has been the number of Braille cells requirement. Any standard Braille display on the market today, and to be competitive, has at least 7, most of the time 14, even up to 28 working Braille cells. So this number is very important to us. And it is important, it's the most important part of a Braille display are the Braille cells. So we've been focused on this requirement right here. As well as our constraints table, the Braille standards have kind of been a looming thought in the back of our mind within our progression. Just knowing that we're going to eventually have to scale everything down to tiny measurements increases the complexity a lot. And so again, this has just been a constraint that has been dictating how our progress has been going and what we need to think about going forward. This is just a system level overview. This is useful us to kind of step back and see that there are a lot of components into the project as a whole, and each component can get delved down into very complex levels. And the problem with us is we've kind of tunneled our vision to only one portion of the system level overview in the actuation scheme and the stepper motors, and kind of perfecting our Braille cell design.
So touching on those actuation schemes, starting with the sponsor given servo motors, we were trying to move away from that. We tried latch solenoids. We decided on the scale that we were going to need them at. We tried a scaled up version and we still couldn't get it working quite right. It just drew too much current and it just did not work right for us. So we crossed those out, stopped messing around with them because we said this isn't going to work for us. Our sponsor recently wanted us to test piezoelectric again. We initially looked into this, did a little bit of research and said, you know, it's expensive. We're going to hold off on that. And we focused most on the stepper motors, which is what we've been working on for the past couple of months. Just to recap on those, essentially you have a cam and follower. The cam profile is what dictates the vertical movement of the follower. And as you can see, we have circular ones that rotate these pins and move them up and down on this profile. And between these two cams and followers, you get every combination of Braille. You can have all 6 pins up, all down, and everything in between. And here is the scaled up 3D printed model that was given to us by the sponsor. Currently, we're running them with larger stepper motors than we will be on the smaller version. And this has basically allowed us to test out all the different combinations, start finding out the Braille patterns of like which ones go down first and then the other ones in every combination and the order in which that happens. And that's important as we need to know that information for when we scale it down. And then we will be able to just type in the degrees that we want it to rotate or even just the pins that are up and down and it'll move to that position. And as you can see on the left side is the open face. You can see all the nice profiles there for all 6 pins. And then on the right side is the cover plate. And what that allows is for us to actually see where they sit in relation to the top plane that the person would be reading. And you can make sure that they're fully down and then fully raised as needed.
So the start to accomplishing the stepper motor approach was first testing all of the components purchased by our sponsors. Basically, the H-bridge stepper motor drivers, again, purchased by our sponsors, and the small stepper motors themselves. And the best way for us to do that was hook up a system like on the picture in the middle there with an Arduino board, because we have familiarity with Arduino branded boards and compatible boards in the Arduino IDE. We had a spare one on hand that we could use and test our components instead of just jumping straight into the Pi that we do not have familiarity with. And we did this basically by just connecting the pins that we can physically connected to the H-bridge and the Arduino microcontroller, assigning those pins to components of a header file in C++ in the Arduino IDE. And this basically just makes digitally writing to those output pins in a more standard fashion, so you have more control how you want to spin those motors so we can get the correct output. And once we both knew that both the stepper motor, the small stepper motor spun, and the H-bridge was powering these, we could kind of translate over to the Pi, get the Pi up and running, because that will be the long-term board that we will use. And this involved translating that code from C++ into Arduino, into Python, into the Raspberry Pi, because that was natively supported. And again, we just kind of translated our code. So you basically just assign the pin numbers that was connected to the Raspberry Pi and the H-bridge as an array, and assign the elements of those array in a library supported by our board and Python. And what this kind of made for us was a sort of test in the software realm. And what you do, you would input a degree of rotation in the console. The code would read that and spin the cam that amount of degrees to produce a new Braille combination. And eventually our goal is to kind of input the Braille combination you want. So the first one there, 1, 2, 3, 4, 5, 6 would be all of them. And it would spin both motors to the correct amount of degrees to produce that combination. What we quickly found with testing is that this might be very difficult, because for 360 degree revolution of one cam, that takes 200 steps with the large stepper motor, which means that each step goes 1.8 degrees, meaning that you're kind of limited. If you put anything under 1.8 degrees, it's going to default to 0. Anything over defaults 1.8. And you're limited to multiples of 1.8. And with the smaller stepper motor, this becomes even more of an issue, because it's a larger number of degrees per step. And so we basically have the precision of only rotating 22.5 degrees at a time. And this basically can result in no combinations being produced correctly.
So here's a video of all 6 pins moving. We just have both stepper motors kind of spinning 360 degrees. And what that shows is that we do have it working. The cams are moving the pins correctly. The mechanical functionality is working. But what we needed to find out next, we have the layouts for both the top and bottom pins, as the cam profiles are the same. The issue are the 2 pins in the middle. They occur at a higher frequency in relation to the top and bottom pins. So we need that finer granularity of the larger stepper motors, and sometimes even finer than that. So we're working on solutions that we'll get to in a couple slides about how to reduce that step size if possible. And then here's another video of just the bottom two pins moving, and this you'll go through the 72, 72, 54, 72, 90 degree rotation to get every combination of these two pins, which is also for the top two pins. And that's important because we need this information so that when we scale down, we know exactly what degree rotation should get us to this setup. And again, that's necessary for our success when we scale it down. And then here is the small stepper motor. The video kind of got messed up a little bit. However, it does spin. It was a pain to solder those little connections on there, and it was very, very delicate. Even one time we were taking it apart and one of the connections got pulled off just by pulling it out of a connector. But it does work, and we were able to measure the number of steps per revolution, which, as Braden said, we found to be 16. And that is a lot more, that's a lot coarser than we need for our use. Again, 22.5 degrees per step. With that 72, 72 type setup for the lower two, 3 movements would get us behind that, and 4 would get us over that. So the pins would not actuate correctly with the current setup. What can we do about it? We can microstep it. Essentially, as you can see in these two graphs, this is without microstepping and that is with. You can see these kind of larger chunks of movement per step. And then on the microstepping, you just have that smooth, almost continuous movement. And the way you do that is by limiting the current to the stepper motor using a PWM signal to the driver. And what that does, it just turns it on and off more frequently so that it doesn't get to a full step. And based on the frequency of the PWM signal, you can almost multiply the steps per revolution into the stepper motor. And so we'll be testing this in the coming weeks to see how far we can push it and see the resolution that we can get out of the small stepper motors.
So the last few slides discussed the software and high-level solutions needed to interface with the stepper motors. But if we want to use them in our design, we will also need to make hardware changes as well. One issue with the stepper motors is their very small footprint. They have tiny terminals that make it difficult to electrically and physically connect them to a larger device. But picture on the left shows one solution that I devised to get past this issue. So the big problem is that manufacturing on such a small scale and soldering on such a small scale is difficult using tools such as 3D printing or other methods. And so I had the idea of using custom PCB electronics that are readily available to order on a small scale. And we can take the stepper motor, put it through the slots on the PCB and solder the terminals in. And by using an onboard connector, we can then connect this collection of stepper motors to a larger display. And this would help mitigate these physical issues. But outside of only physical design, we also have plenty of electrical issues to handle as well. So motors are typically power-hungry devices that require a lot of current, and this is difficult for the Raspberry Pi to supply alone. So we need a device such as a motor driver that will help give the motors all the power that they need. Now, this seems like we've checked all of our boxes, we've thought about everything, but there still are some issues with things like the stepper motor driver shown on the right. In the previous slides, if you remember, we said that each of the 14 Braille cells in our design has 2 motors inside it. And so this means that using 1 motor driver for each motor would need 28 total drivers, which is a pretty big number. And in the next slide, I'll talk a little bit about some creative ideas I had to reduce this number. So like I was saying in the previous slide, like I was saying in the previous slide, if we want to power 2 motors, we either need 2 single motor drivers shown here, or we could use another option such as a bigger motor driver. So in the top left here, we have an example of a dual stepper motor driver that is able to power 2 motors at once. And this sounds amazing. We take one of these, we put it for each Braille cell side by side, and all of our problems are solved. But as you know, nothing comes for free. And so if we want to implement this dual stepper motor into our design, it comes at a cost that is almost 4 times the cost of a single driver, which isn't really feasible for our cost-constrained design. And there's also the issue of the width of the chip used in this dual stepper motor driver. So 6 millimeters seems like a very small number for most scales, but when it comes to the standards of the Braille language, the minimum adjacent spacing of characters is actually around I believe the maximum is around 6.1 to 6.5 millimeters. And so this means that if we were to use the dual chip and place it side by side for each Braille cell, we would run into issues when we place them horizontally and they would run into each other. So after looking at these two options, I was pretty unsatisfied with what was available for our design. And so I knew I needed to get a better understanding of what the motor drivers are trying to accomplish in order to create a better solution. So here you can see under the label of bidirectional, this shows an example of kind of how most motor drivers intend to work and how they aim to work in these two designs as well. So you can see that traditionally the motor would be placed between two parts of the circuit. And here I showed that current can go in one direction, but by manipulating the circuit, you can send current to the other direction as well. And this creates the bidirectional movement of these stepper motors by manipulating the direction of the currents. But if you look above in the CAD rendering of the cam and follower design that we want to use, you'll notice that the profiles aren't really bidirectional. They very slowly go in one direction and then quickly drop off in another direction. So if we attempted to move the cam in both directions, the pins would prevent movement. And this makes the direction of our cam and follower unidirectional. And so if we have a unidirectional cam and follower, then why would we need a bidirectional motor? And so after thinking about this, I realized that we could manipulate the way we connect the motors in our motor driver. And instead of connecting it between the two terminals to achieve current in both directions, we can just use current in a singular direction in order to power two motors from a singular stepper motor driver. And this greatly increases the benefit and value of using the single stepper motor because it's now sufficient for our design. It's much cheaper and it's much smaller than the other options we explored. So going back to the motor bracket that I talked about a few slides ago, here's just a few slides to demonstrate the process I used to develop it. On the left, you can see a concept sketch that I created to get an idea of what features are important in the design. And then after creating that concept sketch, I used a CAD model provided to our sponsor in order to create the bracket for the motor off of that model using already measured dimensions. So you can see here actually in the model that there are a few changes that I decided to go with. So you can see that the motor on the right is actually turned around and facing the opposite direction of the motor on the left. And I believe the sponsor originally thought that this would make the connections easier to make. But after coming up with this new idea, I realized it made a lot more sense to flip both the motors around because the scale that we're working on with this PCB bracket is already very, very small and tedious. And so the more that we can fit onto one bracket, the better. And so I used that decision and then went into circuit design software to create a custom board layout for a stepper motor driver mount. So it has the small slots that the terminals of the device can go into here. And then it has pads where you can solder to make electrical connections, and then ultimately uses a large connector to connect the whole assembly to the Braille device electronics. Here we have an electrical schematic that shows the hardware needed to facilitate communications between the Raspberry Pi Zero device and the stepper motor drivers. The schematic isn't fully complete, but I believe it illustrates a lot of the core components that we'll need to implement a custom PCB electronics design. So on the left, we'll start with the Raspberry Pi header pin connector. This is used to take the development board of the Raspberry Pi and then place it onto our custom electronics. In the middle, we have 3 chips that are basically output expanders. So the Raspberry Pi connector is limited in the number of outputs that it can provide. And so we need another way to generate more outputs in order to control the large number of motor drivers in our design. And so that's the functionality of these central components. And then on the right, you can see a simplified block that shows the array of 14 motor drivers that we have for each Braille cell. Here we have the power stage for our device. So for any compact and portable device, you want a battery that is lightweight and energy dense. And so that led us to the selection of a LiPo battery for portability. And if you have a LiPo battery, you need some way to recharge it. So on the left here, we have a USB-C connector that supplies power to the device. In the middle, we have a battery charging chip because LiPo batteries have sensitive chemistry. So you want to make sure you use a regulated, safe way to charge them. And then on the right, we have a device called a boost converter, and this takes the lower voltage of the battery that we're using and scales it up to a higher level needed for the Raspberry Pi microcontroller, as well as other motor components in our circuit. And so here I decided to repeat the original block level diagram that we used. This is just because as we go into discussion that dives deeper and deeper and deeper into the low level solution we want to create, it's important to take a step back and take a glimpse at the bigger system to have a better understanding of the project.
So that was our progress made on the software and hardware this semester. This is exactly what we did on a scheduled breakdown. Immediately following the PDR presentation, we made component selections of motor drivers and stepper motors. And we then found different microcontrollers that we had available to us to begin testing our actuation methods. We started with successfully operating a large stepper motor. We used an Arduino IDE board to do this, and then we moved into operating the small stepper motors. Then we decided that we needed to test and upscale larger Braille cells. So we asked our sponsor to 3D print a Braille cell, as you saw in the previous slides. Once we did that, we needed to find pin operations in different ways to raise all of the separate pins. We're almost done with that. We have the top and bottom pins completely figured out, but the higher rate of the middle pins is what we're currently stuck on. Moving into next semester, we decided that we need to use the small stepper motors to make small Braille cells. And we know that we need to microstep the motor inputs in order to do this using PWM. And we're going to have a small Braille cell printed for us. We also need to work on piezoelectric cell testing. Our sponsor decided that he wanted to go back into piezoelectrics because he didn't mind the cost that we first thought was an issue. So he's purchased exact piezoelectric cells and piezo strips that he would like us to functionally test when we come back in the second semester. Immediately following this testing that we're going to do at the first 2 weeks of the second semester, we need to get a move on our board that we're going to print out. We need to make a decision on what we're going to be using for actuation, if piezo is where our sponsor wants to go with, or if the stepper motors do work on a small scale. And then we need to get those as quick as possible so we can then begin assembling, testing our system performance. This is our current milestone table. We are currently doing the CDR presentation, and identifying the pin actuation positions of the large scale Braille cell is something we hope to have done by the end of this week. Then moving forward to next semester, as I've stated, we need to get a small motor cell spinning and functionally test the piezo strips. That way we can begin ordering custom electronics and functionally testing our design. Since we've last met, these are our updates to our milestone table. We added this presentation here, and we also added that we need to identify pin actuation positions. We didn't exactly realize that that was something that was going to be very important once we got a large scale Braille cell working, but that is something we're doing now. And getting a small motor cell working and piezo strip testing is something we're going to do at the beginning of next semester. We have removed getting multiple motor cells spinning because we realize that that's something we don't exactly need to do right now. We need to make sure that we can scale our actuation down to one cell before printing two large ones. And recognizing a connected module is something that's kind of out of scope for where we are in this project, so we've removed it as well. Our spring semester plan is to complete the large scale prototype and assemble a small scale prototype, and then we need to take a step back and ask, are all 6 pins under full user control with our actuation method? If they're not, then we need to go back to the drawing board and make another large scale prototype, edit what we've done in our actuation, and move forward in this process, hopefully in the end, assembling and testing a solution. Some lessons learned this semester are management lessons would be having a poor understanding of the scope of the project will cause delays. Around the middle of this project, we kind of had a poor understanding of where we were going. We were just testing motors and doing stuff like that without stepping back and realizing, is this the right direction? So now we feel like we have a better grasp of our direction moving forward of researching the small scale cells. And we also realize that having intentful and effortful research is needed early on in the project. We did a lot of research on our solenoids and our stepper motors, but we didn't do a lot of research on other ways of getting piezo strips, which now is coming back, it's coming back to us, which we could have saved time earlier. And the quick discovery of a failure is essential. We learned this lesson through the solenoids. Our first 2 days of testing the solenoids, of making them, we learned that there's too much power loss, too much current loss, and to scale those down would not be reasonable. Some technical lessons that we learned are large scale issues will become greater when sized down. If we can't find proper pin actuation positions of the large scale Braille cell, then finding them on the small scale Braille cell will be way more difficult. And we need to take that into account moving forward, and that proper research can save a lot of headaches in the lab. When we purchased our components of the motor drivers and the stepper motors, we kind of just went into the lab and started throwing them on a board and messing with them. If we had done some more research on exact ways that we can get those to work, we would have saved several days in the lab messing with those and getting them to spin. So we have had a plan this whole time to produce a working device, but moving forward, we realize this plan is more flexible. The research of this project versus development is going to be way more important. And we know that we need to take a step back and realize we need to just learn from this experience, develop as engineers as we finish this course. We would like to, in the end, get a working product, but we know it's not the most vital thing for us as long as we're researching and eliminating ways of actuation. And we know that our sponsor is on board with this, of just researching and eliminating ways. So that's what we'll be doing in the second semester.
Any questions?
Yes, a lot. I mean,